So to start off, I'll log into my account with Google. Select my account. And here we are on the home page with the live video feed. Now logged in as me, I've trained my own model on Lola with 235 images. It's fairly accurate, 95.6% mean average precision. Other values are pretty high too. So that means that when we show the Raspberry Pi's camera a picture of Lola, it shouldn't buzz because it recognizes her. So to demonstrate that, a couple of different pictures. First one we'll try is a picture of a cat. The prediction it makes is a Bengal cat. So the Pi goes off. Try it again with a picture of a different dog that isn't Lola. And it beeps. But now if I show it a picture of Lola, it should recognize her and not buzz. So we get a prediction, dog, pug, and no buzzer. Go to my captures, we first showed the cat. So there's our screenshot for the Bengal cat prediction. We go to dog. There's a picture of Maggie. There's a picture of Lola for the two different dogs that we showed the camera. I can also take a manual screenshot. There we go. And I can activate the buzzer manually. Hello, and welcome to this technical explanation of my final year project. In this presentation, I'll first use a demonstration to provide an overview of what the system is and what it does. The system is called RAID, short for Real-Time Animal Identification and Deterrence. It consists of three separate but interdependent parts: a web client, a middleman server, and a Raspberry Pi fitted with a web camera and a piezo buzzer. It's designed to use computer vision to allow pet owners to train a custom model which can recognize their pet, enabling the system to differentiate between one animal and another, and even between individual animals of the same species. If RAID detects an unrecognized animal, i.e. an animal that isn't the user's pet, it'll trigger the Raspberry Pi's piezo buzzer to scare the animal away, acting as a pest deterrent. The first thing that happens in setting up PassportJS is to call the initializePassport function. In that function we set up our three distinct passport strategies. The simplest is a local strategy, which uses the authenticate function provided by the Passport Local Mongoose plugin to authenticate a user based on their Mongoose schema. The second strategy uses Google OAuth or Open Authorization version 2, and in there we pass a unique client ID and client secret for our application, which I've created to the Google Cloud Console, and we pass a callback function which is triggered when the Google authorization completes. At the end of this function we use this find or create function, which is also a plugin I've added to the user schema, and that searches the database for the user who tried to log in, creates them if they don't already exist, and passes them to the login function if they do. The final strategy is JWT. I use this for extracting tokens received as part of the request from the client. The tokens are JSON web tokens with user data encoded into them, and the JWT strategy decodes that data and uses it to determine whether the user exists or not. Moving into routes/auth.js. So in practice, these strategies are used as express middleware. When the user tries to log in using the login endpoint, before we pass them through to the function which logs them in, we first use our Passport local strategy to authenticate them. In the same way, when a user logs in with Google, the Google strategy authenticates them and then uses the callback function to create a JSON web token for them, encoding their data. Finally, we use this get workspace details and create workspace details function, and these create a unique RoboFlow project for the user if they don't already have one, and that'll happen if the user logs in with Google or using email and password. In terms of the live video feed, to receive video from the web camera, the Raspberry Pi uses OpenCV for Node.js, which provides Node.js bindings for OpenCV, allowing us to use the native OpenCV library through Node.js. Specifically, we're using a fork from GitHub user URLCH, as the original repository isn't maintained anymore. In this library, images are encoded to base64 strings and sent to the server over Socket.io, which in turn sends them to the React client, again via Socket.io. And this type of streaming is known as motion JPEG, because it isn't truly a video, it's just a very fast stream of images. So the functionality starts in the Raspberry Pi. The middleman server is hosted on Heroku, so the Pi connects to it via the Socket.io server. We run this set interval function every 500 milliseconds, calling the run video detection function and passing 0 and classify image as its parameters. These parameters are the video source ID and a callback function. Moving into the run video detection function, run video detection awaits its callback function, passing in the video source value of 0 and a delay of 1 second, and when grab frames has finished, it passes its result into another function called detect. If we move into grab frames, obviously the Raspberry Pi server is meant to run on the Raspberry Pi, but just in case somebody is running that on Windows, I also account for that by checking what OS they're using. If they're using Linux, I use Video for Linux to access the camera feed at dev/video0 and use this GStreamer pipeline to resize the video to 640 by 480 at 30 frames per second. The OpenCV build I'm using with OpenCV for Node.js uses GStreamer under the hood for accessing the video feed, which is how I'm accessing the camera using the GStreamer pipeline. Grab frames then just waits for a frame to be captured and uses that delay to make sure the frame has finished processing before it gets another frame. And that's how we end up with a constant video feed. When it's finished, it calls the onFrame callback, which, as we said, is the detect function. We've moved through a few layers here, but within server.js originally we passed classify image as that detect parameter. So moving into detect.js, I'm going to come back to this function to explain how the custom animal detection works, because it goes through this. But in terms of the live video feed, this function just returns an image encoded into an array buffer. So since our function up in server.js is being called every 500 milliseconds, we end up with a reasonably fast stream of images. So back in server.js now, when we get one of these images from detect.js, we convert it from an array buffer to a base64 string and emit a Socket.io event to the middleman server so it can receive that image. And then on the middleman server, it emits its own Socket.io event to the React client with that image. And in this way, we can receive a video stream on the React client over the internet by passing images from the Pi to the server and then finally to the React client. The next thing I want to explain is how the client is able to trigger the Raspberry Pi's buzzer over the internet despite the middleman server and Raspberry Pi having no direct knowledge of one another. The solution was to use MQTT. That's MQ telemetry transport. MQTT is used for sending small bits of information in low bandwidth environments or when you're dealing with slow hardware. It's especially useful for things like IoT devices such as smart home thermostats for sending temperature data across the house. In our case, as well as being a HTTP server and a Socket.io server, the middleman server is also an MQTT publisher, while the Raspberry Pi is an MQTT subscriber. I use the cloud service called HiveMQ, which acts as the message broker between the MQTT publisher and subscriber, which enables the React client to talk to the Pi over the internet. So what happens when you press the activate buzzer button on the front end is we send a GET request to the middleman server's publish MQTT endpoint. Moving into the middleman server, on line 18 here, the middleman server has connected to the HiveMQ instance, and it connects to it using MQTT.js. Down on line 38, we can see that when a request is received to the publish MQTT endpoint, we publish a message of true to the RPI/buzz MQTT topic and just send back an empty response body. In the Raspberry Pi then, we've also connected to the HiveMQ server, but instead of publishing messages like the middleman server, we subscribe to the same topic that the middleman server publishes to. Then, when a message is received, we call the buzz function. In the buzz function, we just use the on-off library's GPIO module to turn the buzzer on and off every 100 milliseconds for a duration of 5 seconds in total, and then stop. So one of the most important things that this app does is recognize various animal species. And to achieve this, I trained a custom YOLOv4-Tiny model, which is a smaller and faster version of the original YOLOv4 object detection algorithm. And it's ideal for running on something like the Raspberry Pi, which of course has limited hardware resources. For background, YOLO stands for You Only Look Once, and it's a real-time object detection algorithm ideal for things like robotics or surveillance systems. YOLO is based on the Darknet framework, or it was up until YOLOv7. The most recent one was released by Ultralytics, different people, but I use YOLOv4, which is Darknet. It's rather different from the full-size YOLO. YOLOv4-Tiny uses less convolutional layers and filters per layer than the original YOLOv4. So it is faster, but although it's faster, but it can be less accurate. But as I say, it was ideal for the Raspberry Pi. Now, of course, to train the model, I had to have a custom dataset, and I created my dataset based on, you could say, 3 distinct individual datasets. I have the Stanford background dataset, the Oxford Pets dataset, and then I have various wild animal databases that I compiled myself from RoboFlow Universe. In the Stanford backgrounds dataset, I first removed any pictures that contained animals to make sure that these null examples didn't affect the animal recognition. And this dataset features blank backgrounds or scenes featuring people. I left them unlabeled to help the model understand that a relevant object won't always be present, and there are almost 700 of these images. Before I added this data, the model would throw a lot of false positives on empty backgrounds where no animals were present. So for example, it could just be looking at the empty background and it doesn't understand that there isn't always something present worth detecting, so that's the reason for using these blank backgrounds. The Oxford Pets dataset then has a lot of different breeds of cat and dog. That's almost 4,000 images. From this one I removed some of the less common dog and cat breeds based on listings from the American Kennel Club and the International Cat Association. And in my version of this there are around 100 images of each dog or cat breed left. Then for the various wild animal databases, I combined images from 10 different datasets compiled from RoboFlow Universe. And as you can see, I made 3 separate runs at this before I was happy with the data. I had to make some changes. For example, bears were overrepresented in this and some of their images were poor quality. So I removed polar bears, red pandas, giant pandas, and extremely occluded images of bears, animals which weren't actually bears at all, and animated or painted pictures of bears. I applied data augmentation to rename 2 Polish language labels into English, and I merged classes where they just varied based on the capitalization of their names. For example, I had hedgehog and raccoon twice, just with different capitalization. I ended up with around 200 images each of crow, hedgehog, deer, raccoon, squirrel, bear and rabbit. And then the final dataset, I combined all 3 of these. So I combined the Stanford backgrounds unlabeled images with my wild animal images and the Oxford Pets dataset. And I have an intentional overrepresentation of the wild animals in this dataset with the hope that cats and dogs will always be detected accurately, even if the breed prediction might be wrong. But a wild animal will mostly be detected accurately. Because I just wanted to focus more on cats and dogs. It was very important to me that it always recognises cats and dogs correctly, especially. And having this, fairly equal distribution of images was important for me to be able to categorise these images correctly in the screenshot folder when they're taken automatically. The next step was training the model. Now I actually have a separate video on that because there was so much configuration involved in doing that, and I'm going to put that up on the screen now. So the second video that I've linked in this one shows all the configuration steps necessary for getting set up to train a custom YOLOv4-Tiny model on Linux. But once all those steps were completed after around 9 hours of model training, I ended up with these 3 files. I have object.names, a YOLOv4-Tiny configuration file, and the weights value returned from the Darknet training process. So I said earlier we'd come back to explaining this classify image function, so here we are. In this function we import all our Darknet files and we define a minimum confidence threshold for detections, and an NMS, which is a non-maximum suppression threshold, which is used to decide the acceptable degree of duplicate detections on the same object. Then we use this readNet from Darknet function to tell OpenCV to read a network from a Darknet weights file, so we pass in our configuration and weights files here. We then use these getLayerNames and getUnconnectedOutLayer methods to get a list of the layer names used by the model, and then we select only the names of the layers that are actually being used, which are the ones that produce the final results of the model's prediction. The classify image function then resizes the images to 416 by 416 pixels, which is the size expected by the model since that's what I trained them on. And then we turn the webcam image into a blob and pass it into the network. And then we use this net.forward function, which passes that input blob through the entire network to make a prediction. And then, after we've made our prediction, we iterate through the model's outputs and extract the predicted bounding box coordinates, a confidence score, and a class ID. So this tells us where in the image is the object YOLO just detected, how confident is it in its prediction, and what is it predicting that's present in the image. I then filter out detections with confidence scores lower than my minimum threshold of 0.4, and in particular I ignore any detections for American Pit Bull Terrier because I got a lot of false positives for that class. For each of the detections then I use this NMS boxes function on line 73, which runs non-maximum suppression to remove any overlapping bounding boxes with confidence values lower than our NMS threshold of 0.3. That's what we define up the very top where we have our NMS confidence threshold and our overall confidence threshold. And then finally we draw a rectangle on the image where our prediction coordinates are, and we write the object's label value above the box. Down the very bottom, classify image returns an object containing an image, label and confidence score if an object was detected, or if nothing was detected we just return the image on its own. Since the model was and still is prone to false positives, I tried to mitigate against this by having a second inference step in a way. Back in server.js, first up outside our interval I initialize a 30-second cooldown period, a 75% minimum confidence value, a detection window of 5, and our detection interval is just 500 milliseconds, which is how often our interval runs. I initialize this empty detection object and set the last detection time to the current time. Down here on line 98 I check if something was detected by the model. If the confidence value received from the model is less than our minimum confidence, we do nothing, just return. Otherwise, if we haven't detected this object before in the last 30 seconds, we add it as a new entry to the detections array. If we have seen it before in the last 30 seconds, we increment the counter for that object and increase the entry's confidence sum by the current detection's confidence value. On line 118 I'm saying, if the same object has been detected 5 times within the last 30 seconds, go down and calculate the average confidence for that object over its last 5 detection events. If the average confidence value of those 5 detections within the last 30 seconds is above our minimum confidence value, we've more than likely got a positive detection and not a mistake. There are other things that I could talk about here, but I realise that I'm already running over time for this video, so I want to finish by talking about how the image and label uploading process works in the app, because it's probably one of the most involved steps of all. So in the front end, to handle uploading and annotating images, I use the combination of a custom fork of React Bbox Annotator and React Dropzone Uploader. Images are uploaded using React Dropzone Uploader. Their file data and metadata are passed to React Bbox Annotator and stored temporarily in state. The annotator listens for mouse down, mouse move and mouse up events. Mouse down keeps a reference to the XY coordinates of the initial mouse placement, and mouse move constantly recalculates the XY positions of the moving mouse, updating the rectangle displayed on screen. The final XY width and height values are determined when the mouse up event finishes and a label value is entered. That happens down here on line 480 when the user finishes typing their label and presses enter, and that runs the add entry function. In here in the add entry function we combine the XY width and height values from the rectangle with the file data for the currently selected image, and then once that entry's state value changes, a use effect up here on line 60 is called. That iterates through the entry values, transforming the coordinate values. A multiplier value is used to divide the image's original width by the width of the image DOM element to ensure the coordinates are accurate to the original image when received by the server. A new state array is then made by combining the original image data with its new annotation coordinates, and this data is ready to be uploaded to the server, almost. Finally, down on line 492, after the user has pressed the finished button, we set the value of final entries to our submission entries. That's the entries that we just calculated in our top use effect. Once these final entries are set, we use another use effect on line 344. Until now, the submission entries only have file metadata inside them. They don't have actual images. So this use effect on line 344 pairs up annotations with real file data based on the file name value and creates a new annotated files array. And then once that's finished, we have another use effect on line 84 which runs the submit entries function, and that sends the files to the server, and then most of the work takes place on the server. So the heavy lifting of the image upload and annotation process takes place on the server side. And this is where RoboFlow comes in. Now there's more to the RoboFlow integration than just this, but this is the most important part of it. This upload with annotation endpoint is where the images and annotations are sent on to the server, and we use this multer middleware to process the images on the server side. Once we have our images, we create this directory called uploads, and then on line 200 we iterate through all those images and save every image and annotation to the local disk. Inside Save Image and Annotation, for each image file we give it a unique name based on the current time and its original file name. And then on line 154 here, we write the image file to the local disk. We then parse the JSON data from our annotation that we receive from the client, and we run this JSON to XML function. We use this to convert our annotation data into a format that RoboFlow can understand and use it to train a custom object detection model. There are a lot more of these formats available, but the one I'm using is called PassportJS. So in here I take the top, left, width and height values that React Bbox annotator produced, and I convert them into the PassportJS friendly xmin, ymin, xmax and ymax values, where xmin and ymin make the top left corner of the bounding box, and ymax and xmax are the bottom right corner of the bounding box. We place the annotation data into this XML format, this string template, and then we create an XML file from it with this create function on line 135. That's using a package called XML Builder 2. We return the XML file from this function, and back down on line 170 we write the annotation file to the disk, the same as we did with our image file. Now we needed to save the image first before the annotation file, because within the annotation XML is a reference to the name of the image it relates to and the location of that image on the disk. Back down to line 207 we wait for all those files to save, and then use fs.readDir to read the files from our uploads directory. I sort the files in ascending order and then iterate through them two at a time. So I'm taking an image and its corresponding annotation file all at the same time. Every time an image is successfully uploaded, I increment a counter which increases this percent uploaded value on line 230. I use this then to determine which part of the data's three split values the image is intended for. The first 70% of the images will be training data, the next 20% will be validation data, and the final 10% will be testing data. On line 243, for each set of images and annotations we call upload with annotation to upload the image and its annotation to RoboFlow. In here now in upload with annotation, on line 222 of this function, we first upload the image, which just makes an API call to RoboFlow's upload endpoint and uploads the image itself without its annotation data. We wait for that to finish before running upload annotation on line 236, and we need to wait for the image to upload first, because RoboFlow generates a unique image ID which we need to pass into our annotation upload request so that our annotation data is paired correctly with its corresponding image. On line 252 then we use promise.all to wait until the promises from both the image upload and the annotation upload have resolved. Once that's finished, back in RoboFlow.js on line 280 we delete the entire uploads directory because we don't need those local image and annotations anymore. And then we generate a dataset version for those images. This function just runs pre-processing on the images. It resizes them all to 640 by 640, which are the dimensions expected by a custom trained RoboFlow model. We then update the user's account to reflect the number of their most recently trained dataset version, and finally we export the data for training to the YOLOv4 PyTorch format, which is the format that RoboFlow Train uses internally. And now the user is ready to train their custom model. Thank you for watching. I hope this video gave a good overview of how the app works and what it does.